Welcome everybody in the lecture hall. Welcome everybody on Zoom joining us. Welcome everybody watching from the future. So today we are going to dive more into the material of the lecture. Actually, it's a theory week, so it's going to be a lot of math. But don't worry too much. We will take the time to go through it. Before we start with the material, maybe I can give a bit of information. So the exercise sessions are going to start this week, so this afternoon and on Monday. The groups have been created and the TAs have been assigned to the groups, so you can register for the groups if you haven't done so already. One of the groups is a focus group, which is a group, so that's a proposal of VW, etc. That for all the people who might have less of a mathematical background, so some of you are mathematicians, physicists, so things like sets, maps, and so on is something that you know well. For other people from a study program less mathematical, then maybe the focus group is a good place, because the TA is going to really go more fundamentally through this material, and you should really feel free to ask all the questions you want. And by the way, it's also true in the lecture, you can ask questions. There is no such thing as a stupid question, and I'll take the time to guide you through the material. I also wanted to say a few words because, of course, it's going to be also a practical course with exercises where we will use SQL to query some data. And there's many different providers of SQL databases, and we are going to use PostgreSQL because this one is quite close to the SQL standard. So for teaching, it's good. It's also free to download. But to install, it might not be quite straightforward if you directly install it on your system, because there might be differences between Linux, Mac, Windows, and so it can be challenging to debug into each individual case. But luckily, we have a technology that is called Docker that allows us to have a standard environment. It's actually all Linux, but it's going to be embedded on your laptop in the same way for everybody. So what you need to do is look on Google or whatever search engine you use for Docker desktop. So Docker, D-O-C-K-E-R, desktop, the desktop edition. Normally, you just need to click, and make your way through the installer. Just pick the right one, and that should do it. And normally, if you download the zip file that we have on the Moodle, it's a Docker zip file, it has everything in there. One command is enough to make it work. That's the command docker compose up, right? Docker-compose up. Normally it should work. And if it doesn't, we have an FAQ with the most common issues, but typically that's going to be the case for the people who already had a Docker installed before, and maybe the configuration is different. And then we have a magic command that just switches off and on again, right? So you just reinitialize everything, and we have the command on the Moodle. That usually solves, I would say, 90% of the problems, these commands. And if there is anything, it still doesn't work, then we are here for you. The TAs are here for you. You can drop us an email. You can approach your TA during the exercise session, and we'll make sure that everybody can run this system, right? And the benefit is that then you'll be able to directly type SQL queries in a Jupyter notebook and see the results in real time. All right. Any questions globally on the organization so far? I start with the material. All right, no questions on the organization. All right, so I'll go ahead with the material. So I'll take it from where we were last time. So last time I just gave you the goal of what we want to do. We want to have a mathematical construction of relational tables. Tables have rows and columns. We don't want the order of the columns to matter, but we still want the names of the columns to be unique. For the rows, we have several approaches. We can consider that we have sets of rows or lists of rows or bag of rows. So there should be some flexibility. And I also told you that we have some constraints on what makes a table a table. And there were 3 of these constraints, right? Actually, if I can even show them again to you so that to make sure that we're on the same page. So these 3 of you, let me just scroll back to show you on the slides of last week. So the first rule is broken when you have things like this. You basically have holes in your tables, missing attributes, and so on. So that breaks the first rule, right? The table cannot have that. So that's the first rule when it's broken. The second rule when it's broken is that you have a table in a table in a table in a table, right? So that's breaking the rule of atomicity. You can only have atomic values, but you can't have anything structured in your table. And the third rule is broken when you have in the same column values that have different types, right? So here, for example, there's 2 booleans and an integer. Here you have 2 integers and 1 string. So that sort of things is not allowed. And so when none of these 3 rules is broken, right? You have no holes in the tables, you have no tables in the tables, and every column has values of the same type, then we are in the world of SQL. For whom is that clear? For whom is that clear? Yeah, awesome. Plenty of hands. Okay. And so I indicated that in big data for engineers, we break these rules, but in this lecture, we typically don't. We might slightly bend them, but I'll tell you when we do that. Okay, so this is the last slides that I showed you last week, where we have the attributes that are the headers, the column names, and then we have the values that are what we put in the table. And we want to glue that together with the power of mathematics. Just need to click in here. A question for you. Just to make sure that you followed last time. I told you about a principle that separates this table logical level from how it's implemented on disk. Do you remember what this is called? Is it called decoherence, data integrity, strong data typing, or data independence? You can just go to menti.com and type that long code in there. So we have a small majority that starts emerging, actually a consensus so far. Okay, that's quite good. So you can do it on Zoom, or it doesn't play any role if you're in the lecture hall or on Zoom for this. Okay, so that's good. So you followed what I told you last time about data independence. Decoherence, that's from quantum physics. That's when you have a quantum computer and at some point it interacts with the environment and it breaks everything. So you lose the entanglement and your quantum states. So nothing to do with this lecture. Data integrity is, as opposed to data corruption, it's when you start having some errors in the data or some bits that are incorrect and so on. So that's also something else. Strong data typing, that's a feature of a language like Java, C++, where it forces you to have types. Python would be less so because in Python, you're not obligated to declare your types. But anyway, these other 3 have nothing to do with what we are doing, and data independence is what completely revolutionized databases. Okay, now the math. And I hope I will not scare you too much. Well, I know I won't scare the mathematicians, but everybody else, just don't hesitate to ask questions. So mathematics, of course, is thousands and thousands of years old. And in the very old times, there was a bit of hand waving, right, where we were discovering all the mathematical concepts. And then in the past centuries, it became more and more and more rigorous, and a lot of definitions became more formal. And it culminated in the 20th century, in the maybe early 20th century, with set theory and the systematic use of universal quantifiers, existential quantifiers. So that whenever you say for all blah, 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 or there exists something such that blah, blah, blah. And so we have formalized the notion, well, mathematicians have formalized the notion of sets. A set is just something that contains other things, right? So you basically can give them names, like A, for example, would be a set. In that case, it has 4 elements. And so formally, the way you actually reason about sets, like this is an example, that's a set of all the non-negative integers. We call it N. That's another example of set with a set of strings, right? Strings is what computer scientists call some text, right? And these are 2 examples. And formally, hi Marcin, how are you? So we have our moderating TA who is here, and Marcin will make sure that I get interrupted whenever there is a question, especially on Zoom, because we want to make sure that everybody on Zoom can ask questions in the chat. You can write it in the chat, and Marcin will interrupt me. So you are part of the lecture. You can participate and ask questions too. So what I was saying is this little symbol here that means belongs to. Right, and so this is actually what fundamentally supports the notion of a set, right? A set is basically defined by everything that belongs to it, when you can write it in this way. And so here we can say that this belongs to A, this X, we give it a name, belongs to A, the blue circle belongs to A, the red circle belongs to A. Now you might think that's the sort of things we can do in primary school because that looks so simple, but actually it drove mathematicians completely mad. Because as simple as it seems, then you can start asking, can you have sets in sets? Just like, again, tables in tables and tables. Can you have a set that is a member of a set? And then can a set contain itself, right? Can X belong to X? And then a lot of very crazy things start happening with all kinds of contradictions. And everybody was driven mad at that time. There was the hope that we can completely mechanically prove every theorem just using computers. And then all of that dream was crushed, I think, with Gödel's theorem, Gödel's incompleteness theorem. So what I'm saying is that it looks simple. It's absolutely not simple. But you don't need to worry because for relational tables, we don't actually need to go that far. We can just stick to actually finite sets in the case of tables. So that doesn't lead to all these problems. Okay. Just out of curiosity, who heard of Gödel's incompleteness theorem? Right, some of you. Who heard of, let's say, the mathematicians that became crazy because of infinity? Cantor, Hilbert, some of you, right? There's very good stories on the internet about the paradoxes of infinity. And who heard of Russell, Bertrand Russell? Right? Okay, so maybe more of you. Okay, very good. It's actually interesting from a historical perspective. But anyway, we have sets and we have things that can or cannot belong to the sets. That's called an element of a set. For example, we can say that 1 belongs to the set of the non-negative integers, right? Okay. Another example is that the string foo belongs to the set of strings. By the way, the set S, mathematicians, so the N here, mathematicians all call it this way. This is not standard. I'm just using S for the purpose of this course, but it's not a notation that you would find everywhere. Also, and I know for most of you it's obvious, but just in case, because you don't have the same technical background, when we have strings like that, we put them in quotes. That's typically what we do in programming languages, and we also do that in SQL. So the quotes are basically around, but the string is really just, in that case, these 3 letters. FOO is the string, right? It's a string of characters. Okay. Then, with set theory, we have the notion of subsets, where we can have a set that is a subset of another set. And that means that whatever belongs to the first set must also belong to the other one. For example, in that case, B contains the red and blue circle, and B is a subset of A because everything in B, these 2 elements, when they belong in B, they also belong to A. And we write it in this way with the subset. Conventions can vary. For example, in France, we don't really, I need to apparate, yes. So in France, we don't write this little bar here. When we write this, it's meant that it's not strict, right? You might have the 2 sets being equal, but in English-speaking countries and also internationally, we add this little bar that says that B is a subset of A, but it could also be the whole A, right? So it could also be an equality. So that's a bit like lower than or equal to something. So I'm using that international convention. That's a subset. That's an example of subsets. You agree that the set of even numbers, 0, 2, 4, 6, 8, is a subset of the set of integers, right? That's an example. The set of all the names of universities in the world, ETH, Zurich, NTU, Harvard, Stanford, Imperial College, and so on. This set of university names is a subset of the set of all strings. Okay? Everybody with me? Who is bored and find it so easy that, you know, I'm sure some of you, right? Okay, but it means that you're following. And for everybody else, I'm making sure that you're following. So what sets can we use? Where there's some official ones, like B is an official notation, D for decimal is also an official notation, N for non-negative integers is an official notation, Z would be for all integers, S for strings is only in that course, V for values is only in that course, and T for tables is only in that course. These are just a few examples. I'm going to throw at you, okay, let me do that. I'm throwing that at you. These are all kinds of sets that we'll see in databases, but these we'll see next week in the practical session where we'll look at the actual sets that you will have in PostgreSQL. But just to tell you, there's many different sets, right? So dates, times, binary files, so images, videos, and so on and so on. Okay, so don't worry too much about this. Next week, we'll spend more time on this. So we have sets. And I told you last week that we're also interested in repeating elements. An example of what I told you is what if we have a table and there's records that appear multiple times in that tables? What if we want to allow that? Then it can't be a set. Because in a set, you can't repeat elements. Either an element is in a set or it's not in the set, but that doesn't capture a number of times that you're in a set. If you want to also have a concept of how many times is an element in there, then that's not a set anymore. That's called a bag, right? In a bag, you can have multiple occurrences of the same object. In that case, you have, if I did it right, 3 times the orange object, the orange circles, and twice the blue circle. That is a bag. In a set, you couldn't have this multiple occurrence. Okay, so that's a bag. And again, we're going to have sets of records, bags of records. And then we have lists. And mathematically, these would be sequences. Computer scientists call them lists. It's an abstract data type. In a list, the order is important. So in a list, there is a notion of a first element in the list, a second, a third, a fourth. So there is here an order. And again, these 3 are important because you can define a table, as we'll see, as a set of records, a bag of records, or a list of records, right? If your table is a list of records, then the order is actually important. Who is with me? Okay. Then I'm continuing throwing, it's a brush up. Many of you already know that. Concepts at you, the Cartesian product. The Cartesian product needs 2 sets. You have 2 sets. And the Cartesian product means that you try to find all possible combinations, pairs, with 1 element of the first set and 1 element of the other set, right? So here you have 2 elements in A, 2 elements in B. That gives you 4 elements in the Cartesian product of A and B, right? If I have n elements in A and m elements in B, how many do I have in the Cartesian product? N and n, yes, that would be n squared. What if it's n and m? Exactly, n times m, right? So that's called the Cartesian product. Cartesian because of René Descartes, who did the Cartesian product in the context of coordinate systems. When you have the x-axis and the y-axis, then the plane is actually the Cartesian product of the x-axis and on the y-axis. That just says that every point has 2 coordinates. It's a pair of coordinates, the x-coordinate and the y-coordinate. So that is the Cartesian product. I'll come back to this associative part because this is a computer science-y way of looking at Cartesian products. The purest mathematicians would disagree, it's associative, but I'll come back to that and tell you what I mean with that, because it's important for relational databases. Example of Cartesian product, I have 3 universities and 2 Booleans. That gives me 6 possible combinations in the Cartesian products. All right, just an example. Okay, now when you have a Cartesian product, that's also a set. So you have a set A, a set B, then A times B is also a set, so it contains elements. And the elements in this set, that is the Cartesian product, are pairs, right? It's a pair with 1 element from A and 1 element from B. That's an example of pair. ETH Zurich 20,000, the number 20,000, is a pair in the set S times N. Okay? Now, and this is where I'm coming to the associativity, we can extend this concept of pairs to more than two. We can have 3, 4, 5, N elements. Then we don't say pair anymore, we say tuple, right? We say we have a tuple of 3, 5, 10 different values. In that case, it's 4. And the way we write it is we say that we have an element of A times B times C times D. What does it mean? It means that this object here belongs to A, this one is in B, this one is in C, and this one is in D, right? And if you have this, that every one of these 4 tuples belongs to the set in this order, then that here belongs to the Cartesian product A, B, C, D, okay? Now, special parentheses for the mathematicians who are bored. Normally, mathematically, you should have parentheses, like you have A Cartesian product with B, and then with C, and then with D, but that could be ambiguous with this without parentheses, because you could do instead C Cartesian product with D, and then B, and so on. Then you would create a hierarchy in the tuple. And normally, it's not the same thing to say that you see this as a pair with this on the left and that on the right, or as a pair with this on the left and this on the right. So mathematicians would say it's fishy to not have parentheses here, right? It's a bit fishy. But actually it's not. The thing is, when we look at tuples in the context of relational databases, it's just flat. When you look at a record, it's flat. You have 10 columns, you look at your records, there's 10 values, it's a flat tuple, right? And so for practical reasons, we don't put any parentheses in there. We just say A times B times C times D, meaning the first value is from A, the second from B, the third from C, and the last one from D. If you're super rigorous, and again, I'm speaking only to mathematicians here, you could construct that with equivalence classes by considering that some pairs of pairs of pairs are the same as pairs of pairs of pairs, right? So that's just for the mathematician. You can do it rigorously. And if you're not deep in mathematics, then forget everything I said. We just don't have any parentheses. It's associative. We just have A, B, C, D in that order, and 4 values that come from each one of these sets. Who is with me? All right, awesome, perfect. Okay, and what I'm saying here with flattening the whole thing, that's what everybody does in databases, right? You will not find a single database scientist who would not flatten the definition of the Cartesian products in this way. Okay, here's an example, concrete example. We have maybe a set of departments, a set of universities, a set of buildings, and a set of integers. So now I just said set of strings everywhere, but basically you agree that this tuple here that has 4 values belongs to this Cartesian product because this is in S, this is in the second S, this is in the third S, and this belongs to N, right? So we can say that this is a tuple, a 4 tuple with 4 values that belongs to S times S times S times N. Okay, everybody with me? Okay, so I'm continuing with even more complex functions. A function is a thing that associates things with other things. So we need 2 sets to define a function, A and B, right? What happens with the function is that every element of A is associated with one element of B. These are the little arrows that you see right here, right? So for example, you have this object associated with this one, this associated also with this one, totally fine that they're both associated with the same one, this one with the purple one, the blue with the black one. These don't have any incoming arrow, and that's totally fine. This here is a function, right? What's important is that every time you have an element here, there's exactly one arrow that's coming from here, but on the other direction, you could have 0, 1, or 2 or more incoming arrows. Who is with me on functions? All right. The notation mathematically is the set that you come from is A, the domain. And then B, the codomain is right here, and you have this arrow. And for the association of an element with an element, you use this arrow with a little vertical bar in here. That here is basically this visual right here that the F of this, of the green, is purple, and you denote it in this way. Now, mathematical geeks love, instead of writing it in this way, they write it in this way, right? That's a bit geeky. Actually, I love doing that. But if it's too complex, then just write it with this notation, right? So it's kind of b to the power of a, which has mathematical justifications. So that's a function. Everybody with me, right? That's a value function. I'm associating universities with cities. ETH Zurich is in Zurich, EPFL is in Lausanne, UCL is in London, University College, and University of Zurich is in Zurich. That is a function, and there's nothing in Frankfurt just because I didn't have any on the left-hand side to associate it with. And you see again this notation that an element of the domain ETH Zurich is mapped to, so there's this notation here, to Zurich. And this function, the function is basically what is displayed here, belongs to the set of functions from universities to cities. Okay. Now, what if we make it optional to assign, to associate the elements of the left with something on the right? What if it's optional? That's called the partial function or a map. Computer scientists just say map, so I'm going to say map. So it's the same thing as a function, but it's totally fine to leave some elements on the left without any outgoing arrow. For example, here, there's nothing, there's no arrow, then that makes it partial. It's a map. Okay? And that, typically the notation you just crosses the arrow right here, normally vertically, but I wasn't able to find that in LaTeX. So it's slightly oblique, but normally it's a vertical bar, and you still use this to associate. All right, so function, map, are we clear? All right. And an example of map where I'm associating some attributes with some values. So for example, a name can be ETH, city can be Zurich, department can be DMath, and birth date might be empty. So that's an example of a partial function or map. And finally, the third one, so that's a triple, right? There's functions, maps, and relations. What is a relation? It's a further generalization. It's now not only optional to associate an element of the left with something on the right, you might even associate multiple or as many as you want elements on the right. So now there's not even an arrow anymore, I'm just putting a line. So that's even more general than a function. It's called a relation. So you still have two sets A and B, and you just put some lines randomly between A and B, and that gives you a relation. Now, why did I write that my relation is a subset of the Cartesian product of A and B? Here's why. Do you agree that each one of these black lines right here that connects an element on the left with an element on the right, do you agree that each one of these black lines is in fact a pair? Who agrees? All right. So it means that this is a pair, 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 and this is a pair. So this relation is a set of pairs. So do you agree a set of pairs is the subset of the set of all pairs? Right. So it just means this relation contains some, but not necessarily all, but some pairs of the Cartesian product. Who is with me? Right? Awesome. So this is a relation. So function, map, and relation. Now, just so you know, some people call a map a function. They will also call it a function if it's optional. Then you just have subtlety such that the domain of definition, that might not be the same thing as the domain and so on. These are, I would say, technical nitty-gritty. So to keep it simple, I'm just sticking for that course to the convention. A function maps every element of the left to something. A map 0 or 1, either you map it or you don't. So that's a partial function. And a relation 0, 1 or more, 2, 3, and so on. Okay? So function, map, relation. And again, for the geeky, there's a further notation is that basically if you say R is a subset of the Cartesian product, you can also say that R is an element of the power set of the Cartesian product. The power set is the set of all subsets. And so if R is a subset of this, then it belongs to the set of the subsets of the Cartesian product. Now you see why they went crazy, the mathematicians in the 20th century. It's never ends. But anyway, just for completeness, I'm also putting this right here. And here's an example of relation. That's a relation between string and string. So it's just plenty of string pairs. And so my relation right here is a subset of the Cartesian product of S and S. So the Cartesian product would contain all pairs. And it's also a set, an element of the power set of the Cartesian product. Okay, now the next slide should be natural because I told you that once you see that every line here is technically a pair, then you can make it explicit and just list them, right? That is called an extensional definition of your relation. You just list all of the pairs that you have in your relation, and that's the same thing. So you can either display it like this, preferred by mathematicians, or display it like this, which is equivalent. The reason I'm doing that will become obvious once we switch to tables, because you kind of already see a table right here. Who already sees a table with 2 columns and 7 rows here, right? So that's it. That's why we are doing that. But technically, it's the same thing, this and this, okay? Okay, and now here we have an example of extensional definition of my relation, mathematical relation. We have ETH Zurich, Zurich, ETH Zurich, Singapore. Yes, there is a campus of ETH in Singapore. There is University of Zurich, Zurich, UCL London. That's an extensional definition. It's just that instead of listing it like this, I'm using a text, but that's the same thing. That is a subset of the Cartesian product of strings and strings. Who already sees a relational table with 2 columns and 4 rows here, right? So that's the goal. Technically, it's a CSV format for those of you who know comma-separated value. It's the sort of files you can open in Excel to work with. Okay, so you see, you start seeing the relational tables emerge here slowly, right? Which is the goal. Now, I told you when I introduced the Cartesian product and the pairs, I told you you can extend it to more than 2. You can have 3, 4, 5, so tuples that are longer. So we can do the same thing here. Instead of just 2 in a relation, we can say that we pick 3. So this is now, you probably see a table with 3 columns and 6 records, right? And so now all I need to do is use my Cartesian products that I told you can be without any parentheses generalized to plenty of sets. So now if the elements that belong to A, if all my elements in the first column here, they belong to A, that's here, the second column they belong to B, the third column they belong to C, then my relation is just a subset of the Cartesian product. Right? Again, A times B times C would contain all possibilities, but of course we are not interested in all of them. We take a subset of them, a subset with just these 6 tuples. Who is with me? Okay. And even more, that's called an n-ary relation with plenty of sets. We have a name for these sets, A, B, C, and so on. Relational database people call them domains. We call them domains. So this is why I'm using D in here, domain 1, domain 2, domain 3, domain N. These are sets, I just index them. D1 is right here, and Dn is right there. Now I have an n-ary relation. It's basically going to be a table with n columns. And by the way, because that's how mathematicians think, when you define something, you also have to think of the special cases. So of course, we could also have a relation with just one single column, right? One single set. It sounds a bit trivial, but it actually exists, right? So you could absolutely do that, then that's just a subset. There's not even a single Cartesian product in there, okay? But that exists. Just like you'll see in PostgreSQL, you can define tables that have just one column, and that's perfectly fine to do this, okay? All right. Now, there is one more thing that I want to show you because, again, that's going to be relevant in practice. One way to define a relation is to list the tuples. That's the extensional definition. You just say, these are my tuples, this is my relation. But there's another way. You can do it, and then it's called intentional. Instead of listing them, you define it as some formula or criteria or predicates. That means that you make a statement for every possible tuple that you can have in the Cartesian product. You have a predicate that tells you yes or no. Those for which it's yes, they are in the list, and those for which it's no, they are not in the list, right? That's called the predicate, right? So I repeat, we have a predicate on all possible triples. In that case, these are triples. And that predicates for every triple tells you yes or no. If it's yes, then it's part of the relation. If it's no, then it's not part of the relation. Who sees that it's equivalent to either list it or have a predicate? Who sees that? Right? Okay. And you'll see the predicates, we'll use them in SQL because there is a way to select some records in a table based on a predicate that you can express in just one line. For example, you have a list of universities and your predicate can be all of those that are in Zurich. Right? That's an example of predicate. Okay. What do we have? Here's an example of predicate, actually the one I've just said, right? We have a set of universities, a set of cities. And the predicate can basically say yes if the university has a campus in that city and no if it doesn't. And you can check that here I only have pairs that satisfy my predicate that says the left has a campus in the value on the right. Who is with me? Checking, okay. Okay, and so the predicate of ETH Zurich is true or false? True, yes. And the predicate of ETH Zurich Lausanne is false. That would be EPFL, right? Okay. Very good. So I'm done dropping math at you. I hope you're not lost or bored. I mean, those of you who already knew that might be a bit bored. But the point is coming to the relational tables. That is the point. So based on that math that I gave you, we are going to attempt to give a first definition of a relational table based on all these things. That's the textbook definition. We'll see it's a bit problematic, so I'll give you a second definition that I think is better and future-proof, also for big data. So I'll show you that. So let's drop the first definition. So you already saw tables in what I showed you earlier. So now if you want me to make it even more explicit than that it's a table, then you can turn the circles into rectangles, and then you don't even put the lines anymore, and you might even add some headers in there, right? So do you agree that this, what you see on the screen right here, do you agree it's pretty much the same as here, right? That's the same thing. I just turned my circles into rectangles, but this is conceptually the same thing. So who now has the intuition that essentially a relational table, if we consider that it's sets of records, a relational table is the same thing as a mathematical relation? Who sees that? Okay. So that's the intuition. That's the intuition. And now, surprise, surprise, that is why it is called a relational table, because it can be seen as a relation. Okay, so we could do it in this way, and here I make it explicit, the equivalence, the fact that you can see a table with rows and columns as a set of here triples, right? And again, you have domains, D1, D2, D3, domain 1, domain 2, domain 3. And by the way, do you see that we have domain integrity here? Remember, domain integrity means all the values in the same column belong to the same domain. They are the same type. Well, if we define it like this as a Cartesian product, then we have domain integrity, because by definition, all of these are in the same type, the same domain. All of these are in the same domain, and all of these are in the same domain. Who is with me? Right? So we get domain integrity for free right here. Okay. So I use that term domain. I told you that practically we don't say sets, we say domains for what you have in the columns. So it's a database term. So a domain is just a set, right? It's a set of values. And this is what I showed you before when I threw this huge slide at you with 20 different kinds of sets, right? Strings, dates, binaries, and so on. So these are examples of domains. That's everything you can have in your columns. And now the scary definition, but hopefully now it's less scary given what I've told you. A relational table is just when you have a family of domains. So you just have domain 1, domain 2, domain 3, domain n. A relational table is just a subset of the Cartesian product. It's a relation over the domains. Who is with me? Okay. Who is scared by that formula right here? Who understands that formula? Very, very good. Vast majority. So this is it. So either with the cross or this is just the fancy notation when you're lazy and just want to express it more formally. Okay, so that's a relational table. So now you can see we have a relational table because that's exactly the formula we had right here is the same formula just with strings and strings, right? And now if I don't express it like this or I surround it with fancy formatting that you can do in spreadsheets, then this is a relational table. It is a relation. Now, we also then have a definition of a record. What is a record? Well, it's just a tuple. Remember that the name for an element in the Cartesian product is tuple, so a record is a tuple. Who sees that? Who doesn't see that? Okay, so majority who see it, all right? So a tuple is a record. Record would be the way that database people use. You say you have a table and you have records in there. Tuple would be the mathematical term, but you might use them interchangeably. You might hear people say we have tuples in a table. Technically, the ones who do math and normal forms, they might use the word tuple. But really, you can say tuple, you can say record, you can say row, you know, it's all the same. But mathematically, a record is what we call a mathematical tuple. So I can call it T, and then mathematically, because you have this flat Cartesian product, when you have a tuple T, then T1 would be the first value in the tuple, then you have T2 all the way to Tn, right? And here you have this formula that is boring for mathematicians, but that might be scary for others. We're just saying for every position in your tuple, then the value at that position belongs to the domain at that position. That's when I tell you this belongs to A, this belongs to C, and so on. Everybody still with me? Right? Okay. So this is a tuple. That's a record. It's a row in my table. Right. And T1 in that case, if I take that tuple right here, then T1 is ETH Zurich and T2 is Singapore. So this was Code's first idea, Edgar Code, data independence, to define tables in this way as relations. But it has a few problems. It has a few problems and limitations. I mean, it's great, it's beautiful. One first limitation, and you can see it right here, the columns don't have names. There's column 1, there's column 2, there's column 3, but we don't have names. But you agree that when we have a database or a table, we want to give names to the columns, right? First name, last name, birth date, city, and so on. So that's a limitation, that doesn't allow us to have the names within the mathematical definition. They need to be specified separately. And so that's the first thing. And the second thing is that because of the definition of the Cartesian product, do you agree we have an order in the columns? There's column 1, column 2, column 3, and the order is important. If we swap columns, then that's something else mathematically. But do you remember that I said last week, we don't want the order of the columns to be important. If you have a table with first name, last name, and then you do last name, first name, and you swap the values, that is the same data, right? The order of the columns shouldn't matter. So these are some of the limitations of these definitions. We'd like to have names here, and we don't want the order of columns to matter. And a third thing is that this definition forces us to have sets of records, because a Cartesian product is a set. A relation is a subset of the Cartesian product. So it means that with this definition, we are not allowed to repeat the records multiple times, and we are not allowed to have an order of the records. So we can't have backs of records and we can't have lists of records. We can only have sets of records. Who sees that? Right? So this is my cliffhanger for after the break, where I'll give you a better definition that is able to do all of this. So see you in 15 minutes. Do we have anybody, by the way, during the break who wants to present? Yes, you're right. It's a presentation that's for the cars, right? Yes, okay. So if you want to stay, you know the world record that ETH, the group of students broke the world record of it was the fastest acceleration with an electric car, right? Less than a second? Yeah, I remember the ETH president was very impressed with all of this, and the rector too. All right, so if you're interested in this, then come here, and you can present if you want to work with them. All right, so see you in 15 minutes.